So now, let's make things a little bit more abstract again. But again, a bit like with the tree example, we should just keep this in our mind as the kind of basic model, but then we're going to consider a more abstract version. So let's consider some definitions of Markov chains. So we're going to let script X be some countable set. Okay. And then on that we're going to have some initial distribution. So we're going to set lambda be a positive vector whose components sum to 1. In other words, we're putting a probability on each state X. Okay, lambda X is going to be the probability that you start at state X. All right? So in the snakes and ladders example, all the probability you start at 1, so all that probability is focused on square number 1. Okay? But we could choose a random starting position, for example. It doesn't have to be that we start at 1. We could start anywhere we like with some probability. Okay? Next, a transition matrix is a matrix P, X, Y, that is positive and that all the rows sum to 1. Okay? So P of X, Y is going to be the probability that I'm in state X and the next state I go to is Y. All right? Okay? Now, so that's all the kind of parameters of a Markov chain. That defines all the parameters that we need to know about. Okay, so we have an initial starting place and then a way of moving from one state to the next. All right? Now, the definition of a Markov chain is we say a sequence of random variables, xt, is a discrete time Markov chain with initial distribution lambda and transition matrix P if, for a sequence of states x0, x1, up to xt plus 1, lambda, oh, and a slight typo there, that should be lambda, it should be lambda x0, so I do make typos, so it's lambda x0, all right. So the probability we start in 0 is given by lambda x0, okay, and then given I was in x0, x1 up to xt, what's the probability that I end up at xt plus 1? Well, it's just the probability I go from xt to xt plus 1, ignoring all of this past information. All right? And that is given by the entry, the xt plus 1 entry of this matrix P. All right? And you can notice from this, I can construct all the marginal distributions and everything that I like with respect to this Markov, this process X. Okay, so it's enough to completely classify the whole distribution of this random vector. Okay. All right. So this condition here, as we say, is called the Markov property. So in particular, this equality here. All right. That when I'm at some state x, and I'm going to go end up at state xt plus 1, I can forget all of the stuff from the past. It's called the Markov property. Yeah, it states that the past colours are all over the place today. States that the past and the future are conditionally independent of the present. Okay? In other words, once I give you what's happened currently, okay, this converts this into something more of a symmetric statement. So far we're sort of stating it asymmetrically. What it says is, if I tell you what's happening now, the current state of my Markov chain, everything that's happened in the past and everything that's happening in the future are independent of one another. Okay? Think of this in terms of the dice throws. I've told you where I am. Let's say 10 goes out of the game. All right? That tells me something about all the dice throws that have happened in the past, okay? But there's still some randomness there as to what happened. And my current state, along with the future dice throws, tell me something about the future. But the dice throws are independent, okay? So all those dice throws that you use to construct the past are independent of all the dice throws that you use to construct the future in the Snakes and Ladders game. Okay, so the past is independent of the future once I've decided what the present is. Okay? Okay, so why might that be useful in our dynamic programming example? So remember in the tree example, or the way we went about solving a dynamic program, we were using this sort of separability property. Okay, we were sort of saying that we were solving backwards in time, okay, and that once I sort of conditioned on some of the variables there, remember that when we took the maximization inside the round brackets when we were doing Bellman's equation, we were using sort of a separability property of the actions, that they only had a certain influence on the future events. Okay? That's going to work very harmoniously with the idea of a Markov process, because we're going to, when we take a certain action, and we can use the Markov process again to kind of decompose the process, saying that once I've made my decisions, the past is independent of the future, and I can use that in my kind of separability properties to construct a similar proof of the Bellman equation, right? So there's something that works together quite well there. Okay? All right. All right, so there's a bit more discussion. I think I've basically said everything that's there, so we'll keep on going. You can read that yourself. Another point to make, which I'll state, but I'm not going to prove. You can look up the proofs of these in the notes. So if I take a function, f, okay, I take a state x, okay, and I'm going to take some uniform random variable on 0 to 1. I use that function to give me another state, okay. So there's a function of my state and some random, independent random, let's say coin throw or dice throw. There's uniform random variables representing what the dice was doing in the board game. I can construct a Markov chain by basically taking the current state, applying an independent uniform random variable, okay, and then I get the next state, all right? So whenever I take a function that takes the current state, applies some independent randomness to it to give the new state, I've got a Markov chain, all right? That's what this result says, okay? I've got a proof written up of that, and I'll have it in the notes, but I don't think it's really worth going through now, but that's a fact, okay? It's just saying that this idea of the board game generalizes, that you have the state, independent randomness, that determines the next state, okay? All right? And note how remarkably similar this looks to our plant equation, all right, for the dynamic program, okay? So it's like basically a plant equation, but with some randomness in it, okay? And no actions yet, all right? Another thing to say is that I can make any Markov chain this way, all right? If you give me an initial distribution and you give me a transition matrix, then I can come up with a function that is going to generate that random variable, okay? All right, so that says two things. One, it says that that intuition that we developed from the snakes and ladders game continues over to any Markov chain that we like to consider. It also is a useful thing if we're going to work numerically, okay? Because it's very easy to generate independent uniform random variables on a computer, all right? So what I can do is I just take a function and a bunch of uniform 0, 1 random numbers, and I just iterate using this a set of equations, and I can construct any Markov chain that I like, all right? So I can simulate a discrete time Markov chain very easily as well, okay? Right. Getting a little bit deeper, and I think you will cover this when you do stochastic differential equations, but you'll do it for stochastic differential equations rather than for Markov chains. I'm not quite sure what gets taught where and when. But if I take, there's an equivalence between Markov chains and martingales. So you've done lots of things on martingales, haven't you, in the first semester? All right? Okay. So if I take a sequence of random variables x, okay, and I apply some function to it, this f is not the same as that f, by the way. If f of x of t minus f of x minus some matrix applied to this function. Okay, if that's always a martingale, yeah, then x is a Markov chain. Vice versa, if x is a Markov chain, then this guy here is always a martingale. All right? That's actually a very deep result about Markov chains that can be used for all sorts of useful reasons about their convergence, about their construction. Okay, so this is results that kind of followed from the 60s when stochastic differential equations were first defined, that they were used with these kind of martingale techniques. Okay, it's going to come in handy that there is a martingale view of a Markov chain later for some of the proofs. Okay. In fact, given that you've done martingales already, I'm going to make that an exercise for you. Okay. That means that we get to cover it in the tutorial class. Okay. If you dig around on my webpage, you probably have to find the proof of that. So don't think I'm just trying to be really mean asking difficult questions. Or if you get James Norris's book, you'll find it in one of the chapters there as well. So you know, it's not that bad. I just want you to read the proof. Okay? Right. So now, keep an eye on the time, yeah. Okay. So now let's get to the point where we haven't been writing a lot down so far. Now we're going to get to the point where we're actually proving some things. Okay. So I want us to kind of have a good intuition on how Bellman's equation is going to follow when we go from a dynamic programming setting to Markov processes or Markov decision processes setting. Okay? Now, remember that in our dynamic programming situation, when we had the optimization for that, we were maximizing the sum of rewards. Okay? So one of the things that's going to be very useful for us is things like this, where we're going to maximize the sum of some function r, which is representing our rewards, okay, from time t equals 0, let's say just indefinitely, okay. So I've got some. So what we've got here is I've got a Markov chain x, okay, and I've applied some rewards to it. I get a reward for each state that the Markov chain is, and I'm summing up all the rewards from time 0 to infinity, okay, and then I'm applying some discount to it, beta t, all right? So you commonly come across discount in finance because that's your rate of interest, isn't it? So you kind of have an interest, so the money in the future counts a little bit less than the money in the present, okay? So we're looking to look at the sum of all the rewards accounting for some inflation beta, all right? And I want to be able to characterize what these reward functions look like for a Markov chain, okay? And what I can find is they're actually the solution to a certain matrix operation, okay? So I take my rewards. It must be that the reward function is something that solves the following equation. That rewards are equal to beta times PR, which is the transition probability matrix applied to the function r, okay, plus the instantaneous reward, okay? So what does that actually mean? Well, what this really means is this, what is this really? This is r of x, that's that, plus beta, okay. What is P of R? Well, that's really taking the probabilities of all the rewards given I'm in state X. So given I'm in state X, what is the expected reward of the next state? Okay. Oh, and it should be a capital R. Apologies. It's capital R here. What is the expected reward of the next state? Okay. So what does that remind you of? So that should remind you of the Bellman equation. Okay? Remember, the Bellman equation was the optimal reward was, say, the maximization or minimization of the instantaneous reward plus the reward for the next state I end up in. Okay? So the only difference is I don't have that maximization in here. So let's just quickly recall the Bellman equation was apologies, that should be a W. So it's actually a very similar type of expression. Okay? So when we were considering dynamic programming, Bellman's equation that we derived last time was that the optimal reward is the maximization over the actions of the instantaneous reward plus the reward from the next state that I arrive at. Okay? Well, here we don't have any actions, so there's no maximization to take. It just says that the reward from this function here is equal to the instantaneous reward from this action plus the reward that I expect to get from the next action. Okay? All right. Again, this is a deeper theory of Markov chains and all the rest of it. There's lots of connections here with potential theory, heat dissipation, electrical circuits, voltages, and all the rest of it. Okay, so it plays into a whole bunch of areas. But here we're going to be using it mostly for this dynamic programming Markov decision processes setting. Okay? Right. Right, so let's answer this question. And it's really simple, the proof. So we're going to show that if we've got a Markov chain and this reward function, it must solve this equation. Okay? So, well, R of x, we know, is given by this sum. Okay? So let's just take out the first term of the sum. Okay? The first term is little r of x. And then what we've got left is the sum from t equals 1 rather than t equals 0. Okay? Then what can I do? Well, one thing I can do is I can condition on the probability of the first random variable. Okay, so I can use a kind of Tower property of the conditional expectation. All right, so this is equal to the expected value condition on the first state being x with the expectation that the next state is x1. Okay? Okay? And now I'm going to make a little change. I'm just going to take out one beta here and pop it at the front. So now, maybe one of you can help me and say, well, what is this? So who thinks they know what that purple term is? Yeah? Yeah, so this is conditional. Here we've got R of x is, given my first state is x, okay, what is the sum of all these rewards? Okay, this is conditional on my state is x1, what is the sum of all the rewards? Okay, so this guy here is just R of x1. Okay, what I'm really using there is the Markov property. Okay, that all that mattered is my current state x1. It didn't matter how I got there. It doesn't matter that I started at little x and went to x1. It just matters that I'm at x1. And that just completely determines the rest of the function. Okay? So this is equal to R of x. Let's just bring that beta out to the front here. E of x of R of x1. Okay? Done. Okay? So if I'm looking into kind of sums of rewards, then I'm really looking for something that satisfies this kind of expression. Right? Then we can show other things. For example, we can show that R is a unique bounded solution to this equation. Right? So just to say why I'm doing some of this, it all seems a bit abstract at this point, but actually all of these components are going to come together to give us an algorithm for solving the kind of Markov decision processes. Okay? So properties like uniqueness, monotonicity, existence, you can use all of these facts. So we're having like, there exists a solution to this equation, which is given by this function R. We're going to say it's the unique bounded solution to this equation by this. And then we're going to say it satisfies a monotonicity property, where it's the minimal solution to the object that satisfies this equation. Okay? So then we need to construct an algorithm later that finds the unique minimum solution to this equation. Right? And that's the way of finding the rewards that we should be looking for. Right? Okay. So that's just a bit of a look ahead for why we're doing this. Okay? So now let's show that R is a unique bounded solution, okay, to this equation here. All right? So this isn't too hard. Again, you'll see this exact same idea applied for stochastic differential equations, okay? So you'll do this for stochastic differential equations, and rather than this being some matrix expression, it'll be something like a PDE, okay? So it's much easier doing it for Markov chains than it is doing it for PDEs and diffusions, okay? So you can be thankful that we're doing it this way first, and then you get to see more complicated versions later in someone else's course, okay? So let's take two solutions. R and R hat. Okay, so two solutions to this equation. I can minus the two solutions off each other. So Rx, well, let me just get rid of the x. Then R minus R hat is equal to beta the P R x. Oh, let me do this a bit better. Sorry. Better way to write this. Sorry. Beta P of R minus R hat. Okay. Another way of writing this. Apologies. Okay. And now let's take a norm on either side. We'll work with the infinity norm. So the maximum component, so this is a vector, components given by x. And we'll look at the biggest difference. Okay. We know that's well defined because we said we're looking for bounded solutions. Okay. Okay. This is a sum of this matrix applied to this vector. Okay. And I'm looking at the modulus of a matrix applied to a vector. Right? So I can then apply triangle inequality to each of the terms. Okay? Okay? So here I've just applied triangle inequality. And then I can say, well, each of these components must be less than the biggest of these. All right? So this is the maximum difference between r and r hat, and this is just one difference between r and r hat. So each of these is less than the maximum difference. Okay? Okay? And this is a probability. Probability sum up to 1. Okay? So this is equal to, this here is equal to okay? Now, can anyone see a problem with this inequality, that that is less than that? What did I assume about beta? It's not equal to 0 and it's less than 1. Okay? So if these were different from one another, that would be a positive number. Okay? It'd be like 5. And this is basically saying like 4 is less than 5, because it's saying times that number by something smaller, it's less than itself. So we have a contradiction. It must be r equals r hat. Okay? All right. We'll see these kinds of arguments. Okay, so let's finish this last example, and then we'll move on to the next section on Markov decision processes. Okay. So let's just recap quickly. So we have a reward function, which is the sum of instantaneous rewards at each time from time t equal to 0 and discounted by some interest rate beta. Okay, some interest factor beta. Okay. We've shown that this reward satisfies a certain equation, or matrix equation. Okay. And then we've shown that it's a unique bounded solution to that equation. Okay. And now we're going to show that it's sort of the minimal solution to that equation. Okay. So, in other words, what we're going to show here is that if we have another solution, a bounded function r tilde that satisfies this equation, but with inequality here, then that function is going to be bigger. Okay? That's going to come in handy later, because we're going to find that if we've got, say, a suboptimal policy, then it's going to satisfy an inequality like this. We're going to use that as to help us inform a rule for how we improve a policy. Okay? So this is going to come in handy later in terms of an argument for policy improvement. Also, it's a useful way of characterizing optimality, and in several of the theoretical proofs as well, we'll need to use the basic ideas of this proof. Okay? So it's not so much the statements are important, but the proof idea is important in this. Okay? Okay, so let's prove this. So we'll end up using this kind of idea several times. Okay? So here we're going to show that if this is true, then it's less than the reward function that I wrote up above here. Okay? All right. So by assumption, we have that r tilde of x is less than or equal to r of x plus beta, this guy. And if you remember, this is exactly the same as taking the expectation of the next state given we were in x. Okay, just as before. And then what I'm going to do is I'm just going to apply this again. Let's do it a second time. All right, so I'm sort of unwrapping this expression. It's like a recursion, I'm just unwrapping each term of the recursion. Okay? So notice that this is less than or equal to r of x plus beta e of x. Okay, r of x1 plus beta e of r tilde of x2 given x1. Okay? Why? Because this is just exactly the same expression applied again. So I've applied it once to get this, and then I've applied it a second time to this term to get this. All right? Now let's collect the terms together a little bit. So what have I got here? This above is equal to, I've got r of x0 plus beta little r of x1. Okay? That's these first two terms. Okay? Then, so this is just that. Okay? And then let's collect this guy together. Well, it's the expected value, given I'm in x at time 0, given I'm in x1 at time 1 of r of x2. Okay? So I can use the tower property again to this guy to get rid of this conditional expectation here. All right? So you know from your martingale's course and conditional expectation that when I've got a conditional expectation inside an expectation, it just sort of vanishes, the middle one. Okay? So this is equal to beta squared e of r of tilde of x2 given x. What do you think I want to do now? Sorry? Yeah, continue to do it to R2. And what do you think is going to happen? So I went from having one term at the front to having two terms at the front. So now I have three terms, and the next term would be beta squared r of x2. Yeah, exactly. Okay? And then I'd end up with beta cubed e to the x r tilde x3 here. Okay? Right, you can check that yourself at home, but that's a good guess and it's correct. Okay? Yeah? Or you probably worked out yourself, I don't know. But yeah, great. Perfect. Okay? So if I keep on doing this, what I'm going to end up with after, let's say, t substitutions, is I'm going to end up with sum of t equals 0 to capital T of beta to the t r of x of t plus beta t capital T plus 1 e of x r tilde x of t plus 1. Okay? So what's happened here, I've noticed this is just the first t plus 1 terms of this. All right? Yeah? Agree with that? And then this is just something positive, but beta's less than 1. So what's going to happen to this term as t gets really big? It's going to go to 0, yeah. Provided our tilde is bounded, then this is going to go off to 0. All right? And this, as t goes to infinity, is going to go to what? Rx, capital Rx, okay? And the result we're really using there is monotone convergence, yeah? So if we want to make that mathsy, we'll say this is positive, t is increasing, okay? Monotone convergence theorem says that this converges to capital Rx, okay? So as t goes to infinity, this term goes to R of x, and this term goes to 0. All right? Since that inequality holds the whole time regardless of t, we must have that R tilde of x is less than R of x. So therefore, R tilde of x is less than R of x. Okay? Proof done. Okay? We'll be using that same sort of idea several times. Okay? So it's worth kind of taking a note of that. Not because of the actual statement of the result, but because actually the kind of mechanism using that kind of repeated substitution idea is something we're going to be using quite often. All right? Okay, so that's covered more or less a very minimal description of Markov chains, or just enough about Markov chains to give you an idea of what they are and the places that we need to use them. There's a lot more that one could learn about that. And if you want to learn more, then I recommend one book, okay? And there's also things inside the Bert Seeker's textbook that I mentioned. So are there any questions at this point about this so far before we move on to the next part? Okay.